So this is high performance scientific computing, ME522. So my name is Gaurav Bhutani. I am the instructor for this course on high performance scientific computing, and I work in the department or the School of Mechanical and Materials Engineering. So by training, I'm a mechanical engineer by trade. That's my undergraduate. And by research, I am a fluid dynamist. So fluid dynamist is a person who works in fluid mechanics. So it's fluid mechanics as a field interests me. And that is the reason I'm teaching this course to you, because fluid mechanics particularly is a subject which uses high performance or supercomputers or heavy duty computing a lot. And that is the reason I'm sitting here in front of you teaching this course. Now, particularly going into details of my research, in case some of you may want to get a perspective of what we do in our group or may want to work with us in the future, we work in something called granular flows. So fluid mechanics is a very general and a very, very old field. You may already know that. So these days, in terms of research, granular flows has got really popular. So granular flows is, if you take, for example, if you go to a shop to buy rice or dal, not in a packet but in gunny sacks, they'll pour it for you. Sometimes if you want to crush wheat, so they pour it in a hopper and then it goes to a crusher. So when you are pouring these grains, they tend to look as if they're flowing like a fluid. But when you stop pouring it, they behave like a solid. If you're looking at macroscopically from a distance, right? If you look microscopically, they're just particles. And the laws of collision, the Newtonian mechanics with collision between particles works there, right? So you have some coefficient of restitution and so on. So you can model that very well. But macroscopically, it looks very much like a fluid. And if you look at snow avalanches, which are not that uncommon in Himachal Pradesh, then they are also particles of ice, snow, and some rock particles flowing together. And if you look at it in a video, it looks as if there is a fluid flowing from the top of the mountain all the way to the bottom. So our focus in terms of research area is snow avalanche dynamics. We really enjoy going to the snowy areas, taking pictures, and then simulating that using mathematical equations, which are nothing but partial differential equations. Okay, but we also use some sort of microscopic models to model all these things. So it's a very exciting area. It's a very new area and very unexplored area, but very much requires the use of computing. And when we're dealing with mountain scale simulations, then there are lots and lots of fluid particles, so to say, interacting with each other. So when you write the equations for it, you require supercomputers to solve them. And this is not, fluid mechanics is not related to supercomputers now. If you look at humankind, then what have we always wanted? We've always wanted to predict weather. If you've read this book called Sapiens, for example, it starts with the discussion that we've always wanted. Humans were hunters in the beginning, and then gatherers. If we couldn't hunt it, we will gather some fruits and vegetables. And over time, when civilizations evolved, we realized that we can have a society, we can have a home. We don't need to live in caves. We can set up a home, we can live, but for that we need to control our food. And for that we started agriculture, right? Agriculture, the major issue with agriculture was weather, floods, unexpected rains or no rains at all. And even till today, you read a news that this last month was the driest month in Himachal Pradesh in how many years? We couldn't predict it. When we have reached 2026, we do machine learning and all these things. We have ChatGPT, but still we cannot predict weather. We still get news. We are saying that this was the driest month. We didn't know that, right? So weather prediction has always been a major problem. And believe me not, supercomputers were not developed for machine learning. Machine learning has come up in the last 10 years or 15 years. It's got really popular and really large-scale models and neural networks in the last 4 years with these new architectures and transformer architecture and so on. But the point is that supercomputers have existed for the last 50 years. So they were developed particularly to solve the equations relating to weather prediction. That is fluid mechanics, the Navier-Stokes equations. Okay, so there's a very close relationship between mechanical engineers, or I would not say mechanical engineers, but physicists also work in this, civil engineers also work. So fluid dynamists and supercomputers. And that is the reason, because if you need something, you develop it. If you don't need it, computer science 50 years ago was theoretical mathematics. And still, if you go to heavy, core computer science, it's mostly theoretical mathematics, developing algorithms, understanding algorithms. So these new fields sometimes make us believe that supercomputers are meant for that. Of course, they are developing and growing a lot because of that, but they were initially designed and manufactured for core engineering, particularly fluid mechanics branches. And that was the reason, if you look at the fluid mechanics, particularly the supercomputing labs or data centers, you'll find many people who come from mechanical engineering background working in fluid mechanics, because they have been using it for their work and research. And if you need something, it doesn't work, you go there and you make sure it works, right? So you have to learn whatever is required to get things working with the right team, of course. So I was heading the supercomputing and the high performance computing center here for 5 years, a couple of years ago. So we have worked in it. I've been working in it for a very long time. So I can give you a perspective of high performance computing over the last many years, how things have evolved. And we'll be focusing on the current technology, of course, because there's no point spending a lot of time on history. You can read it if you want. Okay. So the aim of this course is to be able to write effective programs. Effective word is very important for solving scientific problems. I'll come back to this scientific word later in this slide. And the aim is not to be able to write programs which only run on supercomputers. Of course, we will learn how to write programs which can be parallelized on a very large scale or expanded to a very large scale. But nowadays, if you look at your mobile phones, you'll see that it has an octa-core or a quad-core processor. What is the meaning of this quad-core or octa-core? That means your processor has 8 parallel units, so to say, to work together. Because if you work on 8 apps, there are 4 running in the background, 4 in the foreground, then you'll want to make sure that all of them run in parallel, right? So that can only happen if you have some parallel working units called cores available in the hardware. So even your phones can utilize this multi-core architecture nowadays. Laptops, typically, if you buy a decent laptop, you'll have around octa-core or 12 cores available in your processor. If you go to a desktop, again, you might have slightly more number of cores. But if you go to a workstation, which are desktops which have sometimes motherboards with 2 sockets. So they'll have 2 processors in the motherboard. And these are workstation level computers which are north of 5-6 lakh rupees. So the point is that they are particularly designed for high performance computing. But these are still desktops. You're not talking about crores of investment. It's just within reach for an enterprise or a research group, or maybe you people a couple of years from now when you're making a lot of money. So the point is that these desktops can also utilize these ideas that we are learning. If you write a very naive program, it's a serial code which only utilizes one of these parallel cores. But if you are able to utilize the ideas that you learn from this course, and sometimes it's just a matter of spending a few more minutes, and that will be 8 times or 12 times faster, because you'll be able to utilize all the cores available in the hardware. And of course, you can run it on a cluster which is a mid-sized supercomputer, or you can go all the way to these very large supercomputers if you want. So we'll be applying these parallel computing models, so to say, to different programming languages. So what I expect from you is to be able to understand at least one programming language, even if that's MATLAB. Because our aim is not to teach you the intricacies of C++ or Fortran or Python or anything else. The aim is to be able to learn these concepts of parallel computing. And then you can apply it to any language. And nowadays, with the availability of these large language models, you don't need to remember syntax anyways, right? You need to have the idea. If you have the right ideas, you can create the right, generate the right prompts, and then you can come up with the code that you want. Okay, so you don't have to feel stressed about the fact that I don't understand the whole C++ code. That is not the aim. If you understand the idea and particularly understand what we are doing in the parallelization part, that's more than enough. So what I'll do is I'll try to introduce programs both in C++ and Fortran. Fortran because Fortran has been the traditional scientific computing language. It still is nowadays because many legacy codes which are large scale codes still exist in Fortran. And Fortran is maintained these days as well. It's not that it's out of support. So if you buy hardware and you buy dedicated compilers, they come up with Fortran compilers also. Okay. But we'll also introduce C++ because apart from scientific computing, most of the computing at the this low level, I shouldn't say very low level because C++ still is a little high level language. It happens in C++. Okay, so you should be able to identify the statements and the syntaxes and commands in C++. But don't stress yourself with syntaxes. Okay, just focus on the ideas. That's more important. And if you keep doing it, you just remember the syntax. If you type a command 20 times, then it just stays with you. And then Python, of course. I mean, Python is it's there everywhere nowadays. And in BTech, we have first year computing introduced to students in Python now. It used to be C++ long ago, but now it's Python because the world is evolving towards your time is more important than computer's time. Right? So if you are able to write a code in half the time, then it's okay if the computer has to do more work to compile it. Okay, so we'll talk about how to use Python for effective heavy duty or high performance computing as well. And then of course we'll learn about the core parallel computing ideas, that is OpenMP, MPI and GPU based acceleration. Of course you don't need to remember what I'm saying right now. Okay? Of course this is just an introduction. We'll go into much detail in the course that is to come. So OpenMP, just to give you a feel, is when you want to parallelize things on a laptop, let's say. Okay, so that is where you have an octa-core or a 12-core processor, so you can use all the cores. But what happens is the RAM is still the same, right? The main memory is still the same. So it's called shared memory parallelism. But if you go to these supercomputers, large scale, then you cannot fit lots of cores in a given motherboard or a processor. It gets very hot. So what you have to do is you have to use different motherboards with different processors. But each of them have their own address space, that is their own memory. It's different motherboard, right? Different RAM sticks. But then, of course, there has to be some communication between the two. Earlier, the communication was happening on a motherboard. But now the communication has to happen through a wire because there's only a wire connecting these two computers. So that bandwidth of data communication through a wire is much slower than what happens on a computer, on a motherboard, right? And that becomes the bottleneck in that state. So we must understand the computer architecture as well. How a motherboard, what are the different things on a motherboard? How is the networking happening in the cluster? And sometimes you have to explicitly tell the compiler or the executor that use this network, because two computers may be connected through an Ethernet 1G. It may also have a 10G. It may have an InfiniBand connection. So you have to explicitly tell which one to use sometimes, right? So these things are things one has to understand, and that is what we'll do in this course as well. And then once you become an expert in parallel computing and being able to apply these ideas to the understanding of compute architecture and memory architecture and everything, then you have to have some good software engineering concepts as well. I mean, if you're able to understand these things, but still when I say that your code backed up, you said I used my pen drive to back it up yesterday. I do it every 5 minutes. I put in a pen drive, I copy the file. That's not, you use GitHub, right? So the point is that one has to understand the software engineering concepts. Many of the concepts you may already know. If you have lots of files that you want to deal with, you don't want to be manually renaming them. You should be able to write a bash script in Linux or any other OS so that it gets automated, or a Python script which interacts with the kernel. So the point is that these understanding Linux and bash, version control, if many people are working on a project, which typically will happen if you go beyond this classroom, then you should be able to version control, right? People should be able to contribute together. Then debuggers. If you deal with large software, then you should be able to debug codes, your codes or somebody else's code, or your code that you wrote 5 years ago, which looks like somebody else's code who does not know programming at all, right? 5 years ago, you think that 5 years ago you were stupid, and that's a good thing because that means you are growing. Then build systems, make files. So these are things we typically you'll see in any open source software you download. You'll say /configure /make. What is happening when you say /make? Okay, there's a build system. So we learn. It's almost like a programming language, but that is sort of unanimous when you deal with open source codes. So we learn about these concepts as well. Because remember, your time is much, much more important than computer's time. So if you invest in these software engineering concepts, and that will be very brief, I won't spend the whole semester on that, and we'll keep reusing these ideas. That's the whole aim. So if you can save your time through these ideas that you learn, then your journey of scientific computing or high performance computing will be much more comfortable. Okay. So we talked about software engineering concepts, and we've talked about parallel computing. But where does all this happen? If I say cloud computing, if I say supercomputers, you have to send a job that should execute. And where is it happening? This is a hardware sitting somewhere, right? And if you, let's say you interview for a job which is in NVIDIA, everybody would want to work for NVIDIA at least today, right? Because NVIDIA is doing amazingly well. It's I think it's $3+ trillion in terms of its market capitalization, more than Microsoft. The point is that if you interview for NVIDIA and they'll ask you, you know all these things, but do you know what a data center is? Where is this thing sitting on the internet? Where is all this happening? So these are the things one has to answer. So this year we have added a couple of sessions on data centers, because now if you go to YouTube search data centers, you have lots of amazing videos happening. In fact, in India, in Visakhapatnam, there's a new data center campus coming up with subsea cabling. So these clusters or HPC clusters, supercomputers, in South Campus we have one. We'll organize a visit sometime. I'll show you the hardware that we talk about once we do the lectures on data centers. So this hardware sits somewhere, and it may just happen that you may get a job that requires you to be close to the hardware. So what is this hardware? Okay, then we'll talk about the physical infrastructure, the racks. Physical racks that you see there, where you have lots of nodes or blades, as we call them. The cooling system, it's very, very critical. There's a lot of advancement that's happening in cooling system. You don't want to cool the whole room if you want to cool a computer. We can have a system, a closed loop system, where the cooling happens through a fluid which exchanges heat with water, and all this happens in a closed heat exchanger. So you are not putting an AC there to cool this computer. There's a fluid piping going through this computer's hardware to cool it. Okay, so these advanced ideas have come up, and all these piping happens under the floor, and then it goes outside to a chiller where it uses the idea of evaporation to create cooling of water. So the cold water comes back in. It cools the hot oil that was exchanging heat with the processor in the computer. So this is very amazing things or amazing ideas of cooling that are there. So we'll talk about that. Of course, very briefly. I'm not going to teach you a full thermodynamics course. Just tell you what typically is available in the market. Power delivery. How much power do you think does a household use typically in terms of power? So kilowatts. Any estimate? Any ideas? The peak power demand in a house? How much power does the desktop use? No idea? What? How many watts? If you have a graphics card? The net power is 220 watts. 220 watts. So that's a good figure, right? So with the graphics card? Yeah. So 220 watts. So 200 watts approximately. If you put in a heater, this nowadays in your rooms you're putting heater, I'm sure. How much power does that draw? Now you know, right? You have to pay the bill, right? So 1 kilowatt, right? One heater. If you buy a good these hot and cold ACs, they require a little less. They're more they use some other idea where they draw heat from the cold region outside, so they don't generate all the power. So on an average, you use 1 kilowatt power. These supercomputers we're talking about, and I'll give you numbers. I mean, the biggest one is drawing 600 megawatts. 600 megawatts. You can imagine how many homes can be powered using this, and this is drawing that power almost all the time. Okay, of course, this is the peak power demand. Let's say 500, 400 megawatts all the time. So 400 megawatts by 600 megawatts, and this is one system. If you go to a whole campus where you have lots of systems sitting in different areas, talking about gigawatts. A medium scale power plant is of the order of 500 megawatts hydroelectric. This Karcham Wangtu is 1 gigawatt. This is big power plant. So you see the kind of power demand we're talking about. So these are literally drawing powers which a whole big city draws typically, right? So these are not trivial things or systems you're talking about, and they are growing over time, coming up all over the world. So we must spend a couple of hours on these, definitely. Then if you have to use them, how do you use them? You have to send a job, right, on the supercomputer or a cluster. So how do you write a program? What sort of interface is used? What sort of queue system is available? How do you send a job? How do you track your job? What are containers? If you want a new software to be installed on the cluster, you don't request the admin anymore. You set up the software container on your local machine, copy it as a file to the supercomputer or the cluster, and you launch it there. Dockers, you may have heard, right? These are containers. These are like, I won't say a whole computer, whole OS, but the container contains all the libraries and the executables that you need to launch that software. So you can develop these files which are called containers, and if you have, let's say it's a Docker container. If you have Docker installed on the supercomputer, then you can launch the container. Supercomputers typically have Singularity containers for security reasons. So if you have Singularity as a software, which is a very light software installed on your local machine, develop a container here containing, let's say, ANSYS Fluent, and then you copy it there on the supercomputer as a file, a few gigabytes typically, and then you launch the container. You do not need to request the administrator to install any libraries or software. So that's the current way of doing things. So we learn about containers. If time permits, we'll show you very briefly how to develop a basic container, and then it becomes very portable. Cloud computing, which we call infrastructure as a service. You may have heard of Amazon Web Services, right? Google Cloud Platform, Azure. So these are, these supercomputers, they run virtual machines. So what you do is you set up a virtual machine, again like a container, but that is a whole OS in itself. It's called virtualization. So what you do is you set up an OS. Well, they have templates available. You want to do machine learning? Okay, what do you want to use? You want to use PyTorch? They have an image available which is like an OS with all these things installed in it. You just have to click on the button and you say launch, and that will launch the image, which to you looks like a computer that you have just started with a terminal and a GUI, but all that is happening on a supercomputer, which is sitting in a data center. Data center is nothing to do with data as such. I mean, of course, it has to do with a lot of data, but we call it a data center. But that could be a compute-heavy architecture, not just storage place. Okay, so these hardware places, things we call data center. Supercomputer is just the racks in the IT infrastructure. But you have cooling system, you have generators and huge campuses. So all that whole thing is called data center. Okay. So this, so if you want to use computing, you don't have to spend 6 lakhs on a machine if you just want to do it for 2 days. You can literally use your credit card and pay by the second, and you can use these cloud computing platforms. And I'll show you. We will launch an AWS compute image or Google Cloud platform. It requires credit card. So I have to pay for it. So I have to figure out which one is the best these days. But we'll demonstrate to you that it's very easy. Whatever codes we're running on our machine, we launch on those machines and they'll run much faster. And we don't have to spend 6 lakhs, we'll only spend a couple of hundred rupees and we are done. Just have to run one code. Why do you want to buy? And these computers will get outdated in a couple of years, right? But there it's always the latest hardware available. Okay, so cloud computing, we'll talk about that as well. So there's a lot we are talking about, right? And I haven't moved a single slide. The thing is that this course is, I mean, please remember, many people get this idea. This course is not about tools and libraries and all. Libraries and tools will change over time. This course is about concepts and ideas. That's more important. And these concepts and ideas are very same. I mean, they don't change much over time. Tools will change. So we're not going to be stuck to a tool. I won't be teaching you syntaxes related to a particular tool or a software or a programming model. It's all about ideas. So our focus is not on PyTorch. If I say PyTorch, you don't have to mug up PyTorch or CUDA particularly as a programming API. So you understand the concepts, and then if you understand CUDA, let's say for GPU based acceleration, then in the future if something else comes up, you know the basic fundamental ideas. Okay, so we'll be testing you on those ideas rather than syntaxes. Of course, since there'll be a hands-on lab or a lab exam as well, so you'll be expected to write some codes, but you'll never have to remember syntaxes. And if you forget something, you can always ask me, I can tell it to you. What I want to focus on is how you think. So this was all about computing, particularly high performance computing. But then there's also a word called scientific computing. How does scientific computing differ from other kinds of computing? Any ideas? Can you give an example of a scientific computing exercise and something which is not scientific computing? So what about solving a differential equation? Would that be scientific computing or not? Molecular dynamics? Scientific computing, right? For drug design or something else. Numerical methods. What about machine learning? Is that scientific computing or not? Very much. I mean, you are dealing with tensors, matrices. That's hardcore scientific computing. So we'll be spending some time on machine learning or large language models as well. I'll be talking about neural networks with the perspective of high performance computing, of course. But what about mobile applications? Developing a mobile app. That won't be scientific computing. It's computing, of course. I mean, UI, developing a user interface, front end, back end, front end particularly, or web development. So that's not scientific computing. So we'll not be developing apps here, but our aim is for focusing on learning all these ideas from the perspective of scientific computing particularly. And typically these high performance computers are not used for developing apps. They're used for scientific computing only. And that's the reason this course is called high performance scientific computing. Any questions before we move to the slide?
Some of us who are not from the mechanical background, will they face any?
No, not at all. This course is neither mechanical engineering nor computer science. It's very applied stuff. But if you have common sense, which everybody has, and you have the enthusiasm to learn things which you'll not find in any book. I mean, if you look at all this content, there won't be a dedicated book, and actually there won't be a book because these things are changing all over the time. So we have been evolving. 4 years ago, we introduced the course. Now most of the slides have changed because the technologies have changed. The ideas are still the same, but the way I introduce them through a program, the way we do it, it is changed. Okay, so it's very much a function of it's new. Unless you have done it, it's new to you. Okay, so don't worry about it. It's you don't need to know mechanical engineering. I just introduced myself when I talked about mechanical engineering, but it's not a mechanical engineering course. There was a discussion: should we call it ME, or should we call it CS, or should we call it something else? But given that we introduced it, so we called it ME. Right. So the plan for today, which I don't think we have much time, but I'll be talking about course essentials, the grading scheme and all, and then I'll show you a lecture plan. And if you have time, we'll go through details. If not, we'll do it next time. Right. So a couple of notes that we need to discuss in the first class. So this is 3 hours per week. Each session is 1 hour. Although the course says tutorial, so a session could either be a lecture, could either be a hands-on or something that you have to work on, or could be a mix of these things. I might lecture for half an hour, and the rest half an hour you will be doing things that are given to you for hands-on. But it's very important you go back home and try it out yourself if you really want to learn this. Otherwise, this skill over the time you'll forget it. So doing hands-on is something that is going to reinforce the ideas, and this course particularly is very applied. So you should definitely do things and make sure you finish it off by yourself. So we'll be doing it in this classroom, A11 PC lab in North Campus, because I guess most of you are from here, or the postgraduates will soon join. The induction is happening today, so many postgraduates also come, and their labs are mostly in North Campus. For teaching supporters, we have Makesh. Makesh, can you please stand up and show yourself? So Makesh is a PhD student working in our research group. We also have Vishal, but Vishal is not present today. He'll be here on and off. But Makesh is going to be your first point of contact if you have any questions related to attendance or announcements. So make sure you're friends with him. Okay. Thanks, Makesh. So Makesh will be sitting in this class in all the classes, and he'll be remembering all the faces. And of course, if you need help with installing software, obtaining material, he's your first point of contact. You can always contact me, but you'll get reply from me much later than he'll be much quicker in terms of response. Okay. In terms of announcements, we have a Google Spaces group. So please get in touch with Makesh. He will help you add your ID after the class into the Google Spaces. So this is basically, it's through your college account. So it's secure. We don't have random people joining. It's through your college ID. And it's very useful. It's there in your Gmail app on the phone or on the computer. If you just switch on the announcements in Google Spaces, then next time I send you a message, it'll pop up. So make sure you switch it on. By default, it's switched off. So that's very convenient. We have found out, and it's not just for me to send announcements. You can also send messages to me or to your peers, and that brings us to the idea of learning from peers. Very, very important. I can't stress on this more, that peer learning is essential for this course and for anything in here. Then all the slides and material will go to Moodle. That's a learning management system we have here. And all the codes we create will go on GitHub. So that will be a public repository that we'll set up as a part of the class when we learn about Git. And we'll regularly keep pushing the codes there. And then there are some books. I don't know how many of you will find them useful. Many of you will never even open them. But if there are books that I want to share with you, I'll share them through a Google Drive link. Okay. And all the video recordings that we are doing as a part of this class will also go on Google Drive. They will eventually go to YouTube, the processed ones, but the raw ones will go to Google Drive. So if you missed a class, which again, I'm not encouraging you to do that just because we are recording this, but if you miss a class, you can access the recording on Google Drive. If you need it, I haven't shared it, you can ask me. Okay. And then we may create virtual machines, because I don't expect you to install all the software that we discuss in the class on your local computers or desktop. If you try it, well and good, but nowadays nobody does that on a bare metal. You may be installing something as a library and you break something else. So we always do it in virtual environments, or sometimes we develop a virtual machine in itself and launch it using VirtualBox or VMware. And so I'll share a virtual machine that's been developed for this class, which is of the order of a few gigabytes through IIT Mandi Cloud, because that's the fastest in terms of downloading things. So we have a hierarchy of places where you'll have different materials. I'll put all the links on Moodle in announcements. You can go and access that. If you have any issues, talk to Makesh or me in the future. Okay. Before we close, I want to talk about evaluation, and I'll show this again in the next class. So it's a very granular evaluation, but I've seen that this helps, because high performance computing, if I give you just one endsem which is heavy, then if you mess it up, then it affects your grades. So we'll have 2 quizzes, objective ones on Moodle in this room, based on what we discussed. It's purely objective. We'll have one assignment, which will be more of writing a code or commenting thing, or writing some comments in a document. So that is going to be subjective in nature, and this will be on parallelization ideas. Then we'll have 30% or 30 marks midsem out of 100, which will be a mix of objective and subjective. Subjective is basically your lab exam. Objective is on Moodle in the classroom here. Similarly, NSEM will be 25 marks out of 40 objective written, and then a lab exam which requires you to write a code, or in some cases I'll give you a code with some spaces which will be part A, fill it with a function here, so you may have to write that. Okay. We'll have a 10 marks project. Now that completely is driven by you. So after more than half a semester, I'll ask you to come up with proposals. And again, this comes up with what your interest is. I'm assuming many of you will come up with machine learning, which is fine. That's the hottest application of high performance computing nowadays. Whatever you do, come up with ideas, and I'll vet them, approve them, and then you can work on the project. Again, you don't need to spend weeks and weeks on the project, although you can do it, but I expect you to spend around 3 full days, around 24 hours in total on the project while working on it. That's the expectation. So it won't be a huge project, but it will be some sort of a code that solves a scientific computing problem using the ideas that you have learned in this course by either using CPUs or GPUs, whatever you want. Okay. 5% for attendance, just to encourage you to attend classes. Any questions? Now I think it's time, so we'll close the lecture and we'll continue from here tomorrow. So we have 3 lectures. One is, so this is slot C, by the way. The slot C has a class on Monday, which is 10 a.m. You can check your calendars. We have a class on Wednesday, which is 8 a.m. So you have to take it easy on Tuesday evening, and then and get up early on Wednesday morning. It'll be a pain for the first few weeks because it's very cold, but eventually it will get nicer. The weather gets nicer. And then the third lecture in the week is on Thursday at 11 a.m. These are completely slot C timings. Exams, we'll try to hold them in slot C. If not, then we'll do it before the midsummer and sem times. But we'll not change slots, not make it slot free. It's much easier to work with a slotted course. Are you all happy with that? Okay. So thank you very much for that. We'll close the lecture now. If you have any questions, I'm happy to answer that.